Guys, we'll be online with the research crew in just a moment. We're working on through audio video issues as always.
Okay, awesome. So I hope to talk a bit about very specifically what gamma oscillations, and I originally thought of making a superstructure feeding out of this, but it occurred to me that it's a lot better if I link it to things that we have seen before. So we'll be revisiting some papers you've seen before, looking at some new ones, looking at some of my work. I'm going to cherry pick some pieces of this presentation just to sort of like to try to tie these things together. How I think about gamma oscillations, particularly in the supragranular neocortex. So I wanted to start with just revisiting some piece of this this present. Look through this, I guess. Jeff also missed this, but I'm gonna pick also all of this. This is all not necessary learning rules. I wanted to get to architecture. Here we go, cortical columns. Right?
Do you want me to, do we need to shut the window on this? It's pretty dark.
Yeah, maybe it would be helpful to shut the window.
I don't know how much you're going to do
Most of the screen. And a bit more.
Sorry, guys, we are obviously having some audio problems.
With vertical organization and the rough idea about neocortex and the idea that we can build big hypercolumnar networks, right, in a big grid like that. And you have seen visual orientation maps like this from these are two different animals. I think one is a cat and some other rodent. But I forgot.
Like a ferret or something?
Yeah, like some sort, yeah, a marmoset or something. Anyways, so the interesting thing in many of these maps is that you get these patches of selectivity, and more than that, you get these points where all of the different orientation angles of the visual stimulus, wrap around, right? So all possible orientations that are coded here in the different colors, as you can see here.
You're talking about the points where the little points of singularity is not.
Right, exactly. So these pinwheel orientation things here, right? This is a bit more coarse, but it's the same thing. All possible orientations are represented around sort of some central point. And sort of a very high abstract sort of version of doing just that is to organize selective mini columns like that with all the possible orientations around an inhibitory pool.
And are you trying to explain how this comes about or why it's useful functionally?
Both.
Okay.
So since it's a biophysical mechanistic model, it's actually addressing both. But so this is first of sort of a very broad, architectural idea about.
But this is just like how it might come about, right? Yeah.
Right. And so, of course, keep in mind that all of these different circles are still full mini columns, and what I'm particularly focusing on is the highly selective layer 2-3 part of this, which tends to be most active in active stimulus processing, right? This is V1, but this holds similarly true for other sensory cortex. So this was part of a bigger talk about the learning rule behind all of this and how it might tie into this architecture. I'm not going to revisit that. Suffice to say that there's some kind of a heavy learning rule. And what one can do then, just jump forward here. Here we go. That's where I wanted to get to. One can take this abstract idea of an interval-coded organization of units that are competing for activation with a shared pool of strong fast feedback inhibition. And you can take that into a more biophysical model where you're now saying, okay, we now have a big cortical column and it might have 100 mini columns inside of it. And we sample some of them. And those we then simulate in depth. And in fact, we don't just simulate one hypercolumn, but we do a full network of it. And then further than that, you make the argument, look, if there's some kind of Hebbian learning rule in this network, then there's going to be...
So where's the pinwheels on top of this? We've lost the pinwheels.
Right. So the pinwheel essentially is taking away, right? This is an abstract idea.
Yeah, these are mini columns.
Right.
And where is it in here, in this bigger picture you were just showing a second ago?
Right. So
multiple big columns. Go back to
right. This one.
Yeah.
So the idea...
Where are the pinwheels here?
The pinwheels here are the fact that in every hypercolumn, there is one coding mini column for each one of some arbitrary stimuli.
Yeah, but
right, so this is
the
generic.
pinwheels is where you get a combination of all of them, right? So
right, so all of the possible colors are represented exactly once in each hypercolumn.
But I'm not seeing the pinwheel here. So you just jump from that to this, and I'm asking where all that is up to now. You're talking about how the pinwheel comes about in a biophysical way. Where is that in this picture? Or is it not in this picture?
It is in this picture in the sense that every color is represented exactly once in each hypercolumn.
Yeah, but that doesn't say anything about pinwheels, right? Does it?
It means that the hypercolumn spans the full coding space with an interval code.
Yeah, but that doesn't tell me there's a pinwheel. I could have a tiling of every possible encoding and not have a pinwheel. Right, the pinwheel, it's like in some senses that these are all showing each of these as a different color. You don't show me the gray one here, right? So if I'm right, I could have a tiling of all different orientations and not have a pinwheel. So I thought you were trying to relate. I'm just pointing out you were talking about pinwheels and how they come about. And I'm asking as a functional reason for them. And now this picture doesn't show them. This just shows that you've got in every hypercolumn you have a complete set of mini columns.
All right. Okay. So let me go back a step. So this is a very theoretical idea, right? These are abstract units coding for something.
These are mini columns. I understand that. So these could be orientation, division. They could be something else, right? Doesn't really matter. You're just a spatial pool. You're taking an input space. You're dividing into n number of different possible first order features or something like that. And so I understand that. I just didn't. You didn't jump to the hypercolumn and the pinwheels have disappeared. So I'm missing where the connection is between those.
I don't know what you mean by the pinwheel disappears. It's just I'm no longer as strictly schematic in the organization of the minicolumns. They're still all there, right?
Yeah. So I hope you don't mind, but you're going to lose me if I don't get this. The whole idea, okay, you get every hypercolumn has this complete set of a basis set of simple feature distractors. Doesn't matter what it is. And so that's one idea. And sometimes they show that ice cube, and then they show it as this beautiful ice cube, and Bach and has everything. But then when they look down the surface of the cortex, they say, yeah, it's not really like that. It's kind of mushy, and things run around, and you end up with these pinwheels. And the question I've always had is, do the pinwheels really do anything? Are they functional, or is it just the result of trying to map multiple dimensions on a two-dimensional surface, and you just end up with those, and maybe they're not really very meaningful? Big question. So you start off here with a biophysical model saying, hey, here's how these pinwheels might come out. I have all these different orientations, and now they're coming to one point, and I got this thing in the middle. And then you jump to this picture, and it's not there. I'm not sure. These hypercolumns don't say anything about pinwheels. They could be perfectly tiled.
I understand what you mean. This is not about the exact spatial organization of things. This is about the functional organization.
But there's no picture of the pinwheel here at all. I can't even place it here, right? These are just columns.
Well, that's not exactly true, because the point of this picture is that in every hypercolumn,
Yeah.
Every color exists exactly once,
I
like
got
it
it.
would if these were pinwheel organized.
But I don't have to be pinwheel organized and have everything represented once.
Right,
You're showing a spatial
that's the
organization
point. It's
that's
a more
homogeneous.
biophysically plausible version where things are more noisy.
Right, you're showing a schematic that is spatially homogeneous, as opposed to having any anisotropy, which the pinwheel does have.
All right, that is a way to describe that. Yes.
I guess it just seems like at this picture I've lost the pinwheels and I'm not sure if they're important.
Okay. Again, for me, right? We can argue this for a long time.
I'm not arguing. I
Right,
don't understand.
Right. The point of this, right,
Yeah.
picture for me is not that there's a very nice rainbow that runs on the outside. That is not the point. It looks nice,
But that's what pinwheels are.
I understand that is what you focus on. But
No, it's not what I'm focused on. You brought it up, not me. So you brought it up and you're making a point about this. It's okay, what's the point about this? I want to get to the point.
The point about it is that I was trying to make the point that every possible value, right, is represented here, of some attribute, is represented here in an interval code inside one unit. That is what I was focusing on.
That does not require the pinwheel effect.
That does not require a proper pinwheel, but it's clearly inspired by the pinwheel, because the pinwheel suggests that actually every possible code is represented at least once inside a spatially circumscribed
That's not
region.
the way it came about. When it originally came about, people discovered this. They thought it was very more uniform across the surface, and then they later discovered that there was these pinwheels. They're like, oh, look at that. So it didn't go the other way around. So I guess maybe you're saying this is just some sort of evidence that every possible orientation in a visual column would be someplace in a column. Is that what I mean?
Yes, but no, because it goes further than that, right? What obviously this figure here no longer shows is the inhibitory pools. Right? These are only the selected units now. So what you don't see is that the functional fast feedback inhibition, right, is shared upon between singular mini columns for each possible value. So that the point being there is only one red mini column in every hypercolumn, and it shares fast feedback inhibition not with mini columns that have the same selectivity, but mini columns that have a different selectivity on an interval code that spans the whole 360-degree spectrum.
So at a pinwheel, one could easily argue that the mini column would be fast inhibiting with all of its neighboring colors or all of its neighboring things. But in the classic view of a hypercolumn like the Hubbel-Wiesel picture, you wouldn't see that. You would see that they show more of a uniform distribution. So one hypercolumn is one orientation, 10 degrees, the next one, 10 degrees, the next one, so on. And therefore, in the pinwheel, you have this effect that one mini column could inhibit all different types, but elsewhere, you wouldn't, unless you're arguing that the connectivity achieves that anyway.
What I'm arguing for is that there are intrinsic mechanisms, right, that make sure that the competing pool will not have mini columns of the same selectivity in multiplicities inside one hypercolumn.
Yeah, okay. That doesn't require a pinwheel in my mind.
No, but for me, the pinwheel is the best and fastest way to get there.
Okay.
If you want to, in your mind, just so we can like move on from this, reorder these columns into a very nice rainbow inside every hypercolumn.
Yeah, you could have just showed Hubbel-Wiesel classic ice cube block and not mention the pinwheels and make the same statement that I have one.
I don't agree.
But that's what they make. I mean, everyone says that we have one of each type and then it repeats. So that didn't require a pinwheel to achieve that. That was a classic view without pinwheels.
Right, but of course one question is how does one get there in terms of in functional terms, and I will talk about the microcircuits behind this, but I won't get to it when we argue for ages.
I'm not arguing. You just started off with something and now disappeared.
All right. Okay. I'm sorry for being misleading.
So here you have these. So you're saying you have this inhibitory pool within each hypercolumn.
Yes.
Right.
And we will get to that.
But this actually brings up something that sort of assumes these discrete hypercolumn structures as opposed to kind of a continuous sheet of inhibitory neurons, which might kind of span hypercolumns.
Exactly.
And so
which of course leads to the question, what defines the hypercolumn?
Yeah, exactly.
Well, Malcolm showed we've been over that evidence. He showed in his paper, we showed the physiology of the body maps and so on. He would have argued that each of these is representing a specific location on a body, for example, in somatic sensory cortex, and therefore there's an assumption it's not a continuous sheet. Somehow you've got that parcel, that non-continuousness. So I always, in the back of my mind, felt like, okay, if Mountcastle is correct, then there isn't this uniform. Somewhere you have to have an effect which brings upon the hypercolumns as being located someplace, not a continuous sheet.
Right.
So I'm assuming that that's what's happening here.
Yeah, and
our space probably just assumes that there's a mutual inhibition among all these things somehow.
Right.
Okay.
And that's the idea of balanced networks, that there's some kind of general like feedback inhibition that balances the network, which people in physics particularly love, because then there's a lot of like analytical methods you can then use on these networks. I personally don't, because I think it's not terribly plausible, because all of the inhibition, as you have pointed out yourself many times, is incredibly meticulously designed throughout the cortex with all its different inhibitory cell classes. And particularly, I want to talk about basket cells, which are roughly half of the inhibitory cells in neocortex. They're the far most important. So fast spiking, paravalvumin positive basket cells. Why all these attributes? Because the nomenclature on inhibitory neurons is a mess. Because people can't agree whether they want to classify by morphology or by chemical markers or by spike patterns.
Right. But PV includes more than basket cells.
Right. Which is why I'm saying paravalvumin positive, fast spiking basket cells.
Yes. One question. Let's assume the structure right here.
Mm-hmm.
Do you know whether in lesion studies, if let's say something cleaves across one of those pinwheels, whether the network self-organizes to form whole pinwheels after the lesion?
That's a good question. I don't know that, but of course, Mountcastle has some evidence on some of these ideas of organization. That in fact the reason this organization is set up during neurodevelopment, and you get a rewiring in the sense that all columns will stay useful, but you don't get to restore the original neat ordering of things. Right? Yeah. So that with respect to the mapping of different coding columns on the topological organization of the skin, right?
I think the assumption would be, we don't really have enough data on this, but the assumption would be, given the data we do have, I would argue that if I had to take a guess, I would guess if you lesion or damage or rewire, that you will get a similar structure again, but not in the exact same spots. I think that's what
you get some
so this has potential for reorganization, because if you have the
totally.
capacity of these orientations, then you can remap.
Yes, in fact, if you chop out part of the optic nerve that goes to these columns, they start representing something else. So everybody moves around. That's been well documented.
I'm just wondering if in the organization that these orientations are more or less locked into place, but how they actually map into organization.
No, they're not.
Well, I'm talking about the individual hypercolumns. Do they get retrained? I mean, does red turn into a green?
Those are mini columns.
Mini columns.
Obviously, they can, because you can literally swap out the input to this region, put a different input, and they'll still get the structure. So to the extent that the old experiment with the ferrets, where they put the auditory nerve into the optic part, it still works. So these can't be hard tuned to specific input. That's the general assumption. Okay. They would work.
Can we move on?
Yeah, sorry.
All right. So keep in mind, right, these dots that I'm showing are the supragranular extent of neurons that tend to be more recurrently connected and tend to share some kind of stimulus selectivity. So when I'm showing these attractors, right, across minicolumns, what I'm actually mean by that, since it's a biophysical model that does not have abstract minicolumnar units, but instead has biophysically detailed neurons, conductive space, leaky integrate, and fire neurons. These are actually recurrent connections across minicolumns, right, embedded in this big sheet. So that's what's behind that representation.
These are red lines over here.
Exactly, are actually not connections between minicolumns, but then connections between neurons, which are then in minicolumns. Right?
I guess there's so many questions here. Maybe I just stop.
I'm sure. I mean, we can. Yeah, maybe we don't get to gamma.
Just,
That's okay.
just to point out that this picture here, like this, I don't know of evidence to suggest this is a preferential connectivity like this. I mean, we know that these cells, these individual cells connect to all kinds of other individual cells, not just like this.
Right.
And this sort of implies that this preferential red to red thing. Right? I'm not sure that's true. Is it?
Right, and I want to get to evidence for that.
Okay.
Yeah, I think there's a little bit of evidence that suggests that.
Is that the long range stuff we're talking about? The long range laser?
Yeah, long range, but I kind of think of it as if you're learning sequences, bars are more likely to, move.
Well,
in various ways, and then
that
so
are
you-
cutting across here.
Yeah.
That would be the long range layer 2-3 cell tufts.
It could also be like a temporal memory kind of.
Yeah, but the
learning
temporal memory
sequences.
is, it could be, but then also it could be, but, yeah, I mean, if these are actually, like, say, in V1, they would argue these are like a millimeter in dimensions here, you don't see those kind of connections going all over the place over multiple millimeters. So I would say that's not.
Then it'd be the
reported.
layer 2-3 long
Yeah,
range.
but those are very specific, so, in directions, they don't go all directions. Okay, keep going.
Right.
I
So
don't
the
believe that's
modular
right.
recurrent architecture that I'm talking about here, right, is branching over these columns, and it's a nested structure in the sense there is neurons inside, mini columns inside, hypercolumns inside a larger network. All right. So moving on from that to a bunch of PDFs. I probably need to stop share here and then share instead my PDF viewer. Is it here? All right. So let me get to work that a colleague of mine did on this idea. So now this looks a little bit different. This is now biophysically detailed constrained model of exactly these supragranular layers.
This is
so now
we're talking about simulation now?
we are talking about simulation now, right? Each triangle here now represents several pyramidal cells in the supragranular layers, which according to data by people who've been looking at this, right, inside the millicolumns are actually highly recurrently connected. 25% of all the connections between supragranular layer 2-3 cells that could exist actually do exist when they're part of the same coding minicolumn. Understand, of course, that is a functional column, not necessarily an anatomical one, although of course there's plenty of evidence that there's a strong link between the two. And there's some excitatory postsynaptic potential associated with these connections, right? And now every gray bar here is a mini column, and this larger box is a hypercolumn. And so you have these local recurrent connections inside, which we essentially assume are the reason why these neurons are robust coders for the same and share stimulus selectivity, because they're essentially part of one assembly.
So my understanding that that's not true. I have a different hypothesis.
I understand that.
Okay, just want to state that.
Right. That is all right. This is one model, right?
Yeah.
The key piece, though, and the piece that we'll be talking about, is the very strong evidence for these numbers here, right? So the 70% in both directions, recurrent fast feedback inhibition to local basket cells, which tend to not be stimulus selective because they make connections to all the different mini columns, which have different selectivity. So as a consequence, they can, of course, trigger these basket cells and look like they have selectivity, but in fact, their connections are indiscriminate because they just innervate 70% of all the pyramidal cells within their reach, whatever their stimulus selectivity is.
Although there's some recent evidence that seems to point to say it's a little more selective.
Right.
Yeah.
People are now teasing apart all these different groups and trying to decipher what is the difference between intrinsic selectivity based on a preferential input from observed selectivity that is just because you have certain stimuli that activated that basket cell and drove it, right? But again, the point here is that basket cells are very powerful and they connect very prolifically within their local area. In fact, they're powerful enough that when stimulated, they will shut down all the pyramidal cells in their neighborhood, because that inhibition to 70% of the local cells is strong enough to do just that, right? This is the IPSB of minus 2.5 millivolt. You can get constraining data for all of these things from detailed electrophysiological and neuroanatomical studies to estimate these connectivities and these connection strengths. So when we embed this kind of inhibition, it does several things. One is, of course, it does what all inhibition does. It is fast feedback. It can balance the network excitatory state, because as soon as the local pyramidal cells within the reach of this basket cell are active enough, above some threshold, these basket cells will start to fire. They fire non-depressing, very strong IPSPs, and so you will get a strong inhibition as soon as you get too much excitation. So that is a mechanism to keep a lid on activity itself. But more than that, and here comes sort of the pinwheel thing now, is that the basket cell in this model, right, is presumed to be synonymous, right, in its reach with the hypercolumn, meaning that you now have these interval coding units in the hypercolumn that are competing for activation. Because as soon as one mini column is active, it will shut down everybody else. So what does that look like when you actually then simulate a network where there are long-range associative projections to mini columns with shared selectivity, these kinds of projections here, right, which tend to be weaker, right? But so imagine this is a neighboring hypercolumn, right? You think of these as voting connections, right? And we think if there's a Hebbian learning rule, you can like learn these connections. Actually, that's what I've shown in my PhD.
That's true for voting too, right? Voting is a learning.
Right, exactly. And so the fascinating question is, how does that look like? So here's an example now where you have a stimulus. So you are producing some excitation, right, targeted on the mini columns that are selective in your network. So there's two things you're seeing in this plot. So one is the spike raster in the background. Separated by horizontal lines are the different mini columns. So what you see here already is that neurons inside a mini column, right, tend to be active together. That is because of high recurrent excitation inside every mini column. More than that, all of the, when I provide a stimulus, right, all of the of this bigger attractor, this bigger structure that I've formed from all of the mini columns that share this selectivity, only these are being shown here, right, are active together in a longer thing that we might call a theta cycle. So this is like 100 millisecond long activation, and there's several brief bursts in here. And these brief bursts exactly come about because of the gamma. So what's actually happening is that as soon as a mini column is strongly enough, basket cells will fire and will shut off activity. Now, I only show the stimulus selective mini column here, but it's actually shut off across the entire hypercolumn. So if we now take a look from this and look towards a slightly larger network.
Can you go back there for a second?
Yes.
What I'm thinking about is we have this need in our models that the cells that fire quickly, in this case, you're showing all the cells in the mini column, but in context, that wouldn't be true. And but the cells that fire quickly not only have to inhibit all the other cells nearby in other mini columns, but they also have to not inhibit themselves. And so you don't want to shut down everything, but the physiology or the anatomy suggests it would shut down everything because they get feedback too. So we had some earlier work done here where we were looking at how the pyramidal cell and the basket cells get sort of entrained in a way that would prevent it from shutting itself down. And then the question I'm thinking about here is, could the gamma cycle be part of that mechanism? Meaning, like each gamma peak, it's starting over again. It's like, okay, who's going to win now? And we shut everybody down, including myself.
But
And
who's
then-
next?
So I do shut myself down. So I don't need this special mechanism. But then if the basket cell, the duration of the basket cell inhibition, which I don't know what it is, if the duration of that is less than this gamma frequency here, then we'll start all over again.
Right.
So I don't need to have this, I don't need to have this special entrainment between the parameter cell and the basket cell. All I need to do is just start the race over and over again.
Good. Essentially, you've previewed sort of the next 10 minutes of what I'm going to talk about. It's very nice. That is exactly it. So this fast feedback inhibition, right, it's not just fast in terms of strength and connection delays. So these are the fastest synapses that we have in cortex. When I look at these various models that others have built at the Allen Institute, the assembly model that I've reviewed, like
Faster than gap junctions?
no, not faster than gap junctions.
Yeah.
Gap junctions are not synapses in my world, right? But amongst the synapses that deserve the name synapses, none are faster than the basket cells in terms of connection delays and in terms of speed of action. And it's GABA A, so it's very fast. It's a synaptic time constant of like some 4 milliseconds or something, which suggests something that is actually faster than gamma oscillations. So typically people say, gamma's on the order of 50 to 80 hertz or something. Sometimes people separate out fast gamma, which they say is like on the order of 100 hertz. But the point is that still means 10 millisecond delays between the gamma cycles, right? The difference is between one gamma cycle here, right? And
Yeah,
another
the
there.
basket cells are really fast, right?
And the basket cells are really fast. So, in fact, it is exactly true. Biophysiologically, you can make an argument that the inhibition, right, incurred from an activation, which will then shut down the local pool, right, is actually worn off already halfway through. And now, halfway through, you start a new race to who gets to activate. And this is where these attractor models come in really handy because they can explain a lot of what happens. Because of course you need to answer the question. You remember this figure here from a previous working memory model, where you get these population bursts, right? Which is where all the neurons fire that are selected fire exactly once, and then they shut each other down. This is a balanced network with no dedicated basket cells, but instead randomly dispersed inhibitory units with no selectivity whatsoever. So it's just a balanced network. And in this case, you don't get a gamma burst, right? You get only a population spike. Whereas in our model, you do. So where does the re-excitation of the selective pool come from? When the basket cells fire and they shut the local population down, where does the second gamma cycle come from?
Not the gamma itself, but the second population of parameter cells.
Right. So I'm gonna go to this one here again because it has some useful slides on that. I hope that works. So here's now an example where you actually the first part of this you are learning this particular pattern. So you have now mini columns here, right? The mini column is the width of this yellow thing. And they're all sorted here. So these are all the mini columns that respond to this red pattern. And they're artificially stimulated. And I already get these gamma cycles. And it's very obvious here why they restart again and again and again, just because I keep stimulating, right, up here. So this is a forced gamma of sorts, right? Where you see that the local population, let's see the yellow one here, right, a mini column, right, it actually goes to 0 firing rate instantaneously, like in between, right, and then it jumps up again to like 50 hertz over a longer
Is it
period.
really jumping to 50 hertz?
Or 30, 40
Is it
hertz.
just a single spike?
Right. Again, it depends on how you compute instantaneous activations, but yes, it is a single spike.
When I read this here, I said, oh, this is a spike, one spike, one spike, one spike, one spike.
Yes.
And then down here, this has got to be some sort of time average, right? Because you're only getting one spike. So basically, you're
It's
not.
population average, actually, over all of the cells inside the mini column.
So basically, you're just. Well, how do you turn that into hertz? It would be more like a percentage. How many of those cells spike on this particular gamma frequency? It's not a hertz. It's
an exponentially weighted moving average.
Yes, so it is a moving average.
Right.
Yeah. It's a little odd way to think about it. I wouldn't think about it that way.
The point is more, right? The reason why I showed is just that if you force stimulate a network like this, of course, you activate that specific population that you're stimulating, but then the basket cells would kick in and cancel out your stimulation, so you're at 0 hertz again, right? Your cells stop firing for some 10, 15 milliseconds until they go up again and firing rate.
Yeah, I just personally, I felt that calling this a frequency was very misleading. We're talking about very specific codes that are occurring over and over and over again. It's not a frequency. It's not like a rate encoding. We're not. This does not imply some sort of like a variable encoding. It's more of like a reliability of how many of these cells are firing each time, as opposed to. I'm just reacting to that because in our world, each of these is a single spike code over a population of cells. It's not a rate. So I'm just reacting to that.
I understand.
Okay, well, I'm just.
That's all fine.
Well, whenever I see charts like this, I always have to say, what the hell are they talking about?
Right.
Yeah, okay.
I get that.
Okay.
So the broader point is that once you have learned such a pattern through forced stimulation, then the network now has these embedded structures where you see that you get exactly what I showed before with the one like selective population that is activating, but you also see that the competing mini columns, so these are now randomly selected mini columns outside of the stimulated pattern, right? They go silent, both during the stimulation, because the basket cells shut these off, as well as during reactivations. When these patterns activate, the basket cells fire, and they will not just produce the local gamma inside the selective assembly, but they will also silence any competing mini columns.
Why do we get 4 or 3 or 4 in a row there? Why isn't the basket cells inhibiting them in that time? You follow what I'm saying? I got these mini column spikes, even if it's at the top of the gamma cycle, right? Okay, right. The gamma's up, the mini column goes, bingo. Mm-hmm. Why is it able to fire again very rapidly out there? Why is it not just one mini column active until the next peak?
Right. I understand exactly what you mean. So why doesn't it look like the Mongilo-Zollix paper, right? And the reason...
No, I have no idea what that is. And I think
the
question was, why do I see 4 of those in a row?
Right. And it's exactly this. It's the recognition that, in fact, these mini columns are embedded in a larger structure. And this larger structure of distributed columns means that there will be out-of-phase excitation arriving at these selective cells, which biases the network, right? It's a bistable network. It has a ground state, right, with a slow oscillation, which you saw sort of before the stimulation, right, which you saw.
I don't get this. I don't see.
Patience.
No, I think the problem if I'm patient, you're going to lose me, and then I won't be able to understand.
All right.
Go. The point here is, I'm looking at this. I'm looking at one. These are mini columns. I can't assume anything about the other macro columns nearby. I don't know what input they're getting. I can't assume that they're going to support this or not support this. In my mind, this has got to be a local phenomenon to this column, this cortical column. And so I can't just assume that the next cortical column over is going to have the same input and it's going to reinforce it.
Right.
In fact, I assume it can't, in fact.
No, in fact, you can't, but you don't because this network has learned these patterns because there's a heavy learning growth.
But that's interesting because, I mean, with the way the whole thinking we've got around here is that the cortical column is a self-sustained unit. If I just have one of them, it can still do something very functional, useful. And so I wouldn't assume that this is a learned pattern is a little weird. I mean, these experiments, usually these are anesthetized animals getting just, sinusoidal gratings or something. And so is that a learned pattern? I mean, is that what you're saying? I mean, it's a little weird, I guess. What if it wasn't a learned pattern? Would I still get these 4 spikes?
I understand. The idea is that the activity of this network, right, is not just the output of a local circuit, right? Because in fact, columns are collaborating over via lateral connections. And so they're collaborating in various ways, right?
That's part of our model, right? That's the whole voting between columns. But is it true that these experiments are these anesthetized animals and are these sinusoidal gratings? What is the experimental setup here? So that's not learned. That to me is not a learned connection. That's like,
in this model it's learned because it's a simulated model and that's how the model works, right? The red pattern exists here because I stimulate.
I forgot. This is a simulation.
Right. So keep in mind the original background activity, right? This like alpha state, like bubbling along of activity is non-specific. So the cells that are not specific to the stimulation patterns are as active as the ones that are specific to it.
Yeah.
That changes the moment that I force a pattern into the system, right? Where now these activated mini columns will shut down all their local competitors and will learn to wire together both intrinsically within the mini column as well as across mini columns to form these attractors, which are now capable of autonomously reinstating themselves. And the whole reason why patterns can now do what is biophysically observed in actual gamma bursts, that you get multiple spikes from the same selective cells, say 4 or 5 of them over a brief time window of roughly 80 milliseconds. So this is macaque data that I'm talking about now in a working memory task, is exactly that you can decode the working memory item from gamma modulated sites, and that you get these rather peculiar patterns where you get these brief bursts at high frequency where for a short amount of time, selective cells spike, some 5 spikes or something, until they go silent again. And this network model provides an answer to how and why they do this. The gamma oscillation is there because these mini columns get shut off, and the gamma phase reignites because there's out of phase excitation from other mini columns that also are part of this pattern but are out of phase. Keep in mind, right, you see that the mini columns here, they are not all active together. They're out of phase, meaning when one mini column just got shut off by its high activity, right, it will still receive excitation from a different mini column that is on top of its gamma spike right now, right, and will deliver out of phase excitation to this mini column to bias the race such that this particular attractor will reactivate again, as opposed to a ground state or a different attractor that might be trained into the network.
Again, now, if we do talk about macaque and those like, and we're talking about the classic visual experiments, those again, anesthetized animals seeing sinusoidal gratings, and
no, that's not what I'm talking about. I'm talking about working memory tasks. I'm talking about, let me show you exactly what I'm talking about. How do I change this?
Working memory.
Zoom.
Then what part of the
Share.
cortex?
And not this one. Let's see, where did I put it?
What regions in the cortex are they looking at then?
I'm looking for the, where did I put it? That's not this one. I'm sorry, I'm a bit confused. I wanted to show you the macaque data.
Do you know what region of the cortex we're talking about?
Hold on. Dorsolateral prefrontal cortex.
Okay, so
Here we go. Gamma and beta bursts. And what I'm talking about are these very discrete events. So 80, let's zoom in there a little bit. Let's go more. 40, like this, right? Where you see very discrete short events at low frequencies, beta frequencies, as well as these brief gamma bursts, which are very brief events. And you can show that you can decode the memory content from those electrodes that do have these bursts that are gamma modulated.
So what confused me about this, Florian, is that you start off by showing these pinwheels. As far as I know, those are only ever been observed in V1.
Mhm.
And so I thought you were talking about all V1 stuff. I didn't realize you were talking about a
Generic cortex model.
no, but you're talking about a memory task as opposed to a representation task.
Mhm.
And so those are very different things. And so I thought you were talking about, okay, how's visual cortex processing this information and how's it leading to these sort of mini column structures that we see, but you're not. You start out with some justification of that, but now you're talking about this working memory task in higher cortex,
right?
Which is very different.
I understand. I'm a believer in a generic cortex.
Of
model
course, I
that
do
can
too. I
any
do
and all
too.
of
But
this.
the pinwheel thing is not clear that that's been anywhere else. I don't have any evidence for that anywhere else outside of P1. So it may be, but also that it's a very different task. I was under this. I missed it. I thought you were talking about how the basic structure. Now I didn't realize you were talking about a working memory task.
Right.
That's all of this.
Right. I guess it.
Because when I talked about our model, I wasn't talking about working memory task. I was saying, okay, how do these cells? I was talking about the spatial pooler and how that work. It's not a working memory task. So I missed that. Sorry about that.
Yeah, right. I'm sorry. I should have made clear that this is sort of part of a longer series of working memory models that I've been sort of
I
presenting over
understand,
the last
but then
couple of
you
weeks.
start off by showing the basic pinwheels, and that wasn't part of your working memory model. So that got me fooled.
Right.
So what I see is you start off with something where you're trying to explain a structural model, and then you're going up, and then you're transitioning into behavioral model.
Yes, but more than that, right? This is not just a model of working memory performance and behavior. It's also a model of electrophysiology. So you actually want to capture the firing rates, for example, and you want to capture the duration of these activations, and you want to get an understanding of where they come from, and you want to understand why basket cells are important to this, and you want to understand what possible model could explain the re-excitation, like why are there multiple spikes if basket cells are so powerful in locally shutting off activity. And so this model does just that, right? It bridges a lot of different levels.
So it's interesting, in our case, when we think about a sensory cortical column modeling the world, I find I have trouble just accepting that there's these learned connections between every cortical column. That is a function. It's a basic function for an individual column's function, and that goes against the idea of a cortical column as a processing unit. It says, no, I can't understand how it works on its own. It has to be connected in a very specific way to other columns nearby. So that's where I start saying, maybe that's true for a working memory problem, but I have trouble understanding that for anyway. That puts it more into sort of like the voting in our world, sort of the voting idea.
Right. These are essentially the voting connections, are the learned associated.
Yeah, but in our case, a column on its own can form a complete world. It can do its own thing.
Right.
And so voting is an optional layer on top. But here you're relying on those long range connections not as something optional, but as sort of integral to the whole processing of a column.
Right.
Like you couldn't have a single column do this.
Right.
Which is sort of it's maybe true, but it's certainly against sort of the working premise we have here.
Right. It's just that somehow you need to be able to explain, right, like this very basic question, like you phrased it yourself early on, right? Why are there multiple spikes?
Yeah, but I had that even at a primary sensory level. So there's other options to that. There's other ways that could come about besides these long range connections. So that was my assumption all along, and that's why we look for local properties between entrainment between the two cells, or even the idea that the gamma frequency could be part of that is something that's an interesting idea. But then it's when you bring in these long range connections between columns, then it's like, well, wait a second, that's kind of breaks one of the. It might be true, but it breaks one of the sort of premises at which our entire work is based on.
The activity from the other hypercolumns has to be out of phase in some sense, right?
Yeah, which automatically happens as soon as you put in biophysically plausible connection delays, because these connection delays will be long enough, right, to overcome the additional 5 milliseconds or so that you need.
So is there synchronization? Is there synchrony across the hypercolumns, or is there at the gamma frequency level?
So the basket cells synchronize activity inside the hypercolumn, but their spatial reach is limited, so there's no long range synchronization, because for that you would need long range inhibition.
So the gamma activity in one hypercolumn is not synchronized with the gamma activity.
No, it's not, and you see that in these activity plots.
There was I don't know, in the classic literature, I don't know if this has been overturned, but in the classic literature, they made a very clear distinction between two classes of And one has a short range connection and one has a longer range connection. So large plastic cells in the past is a very definitive break. It wasn't like there's a continuum.
Right.
And so I don't know if that's still true, but that's the way it's always described classically. And that to me was all, I thought it was a very interesting clue. It's like, okay, you got this very fast inhibition. One is at a short range. I think it's like, I forget what it is, but it's like, 5 or 8 times larger for the large basket cells. Mm-hmm. So I thought, well, you got these two things going on. That seems to be going to be really important. Right. And so it doesn't seem like there's any recognition of that here, because we're talking about the range of these basket cells. How long, how far are they, how short are they? Well, in biology, there seems to be 2 different ones. It doesn't sound like you're thinking about that here. Is that right?
No, we are thinking, if we were to think about it in that terms, we would think about sort of rather large basket cells that essentially are large enough to reach all the mini columns in a hypercolumn.
I thought that's pretty big. I thought there were, I can't remember now, I have to be careful because I might be making this up, but my recollection was that there was the basket cells were dominated by the smaller ones and the larger ones were fewer. And so
you wouldn't need many of them.
Because they're so powerful.
Yeah, so
exactly.
But there was like there's these 2
different
different stages of fast inhibition going on, and so that's like if that's true, then there's this other very important mechanism which is going to be somehow affecting the whole column versus a small part of the column separately. And I don't understand why it's like that, but that would be, it seems like a very important clue if it's true. It's like you really can't understand this unless you understand why it's like that.
If you buy the argument that the hypercolumn is, like some 640 micrometers also in diameter, then you need to have basket cells that have a radial reach of some 300 microns or so to do this. Yeah. But the neat thing about this mechanism that, to me, right, I'm going to stay away from the term pinwheel, but I'm instead going to use this very nice interval code where every possible value is represented exactly 1, is now very neatly explained by this mechanism. Because now you understand that there's a strong competition, right? If you have multiple embedded attractors inside here, right? So I'm showing just connections of the red one here, but of course, if there are multiple ones, right, then they're actually competing for activation. And you cannot have multiple mini columns of the same activation inside the column because one would shut down the other. And since they would receive inputs at the same time, right, whoever wins out the race, right, will eternally and always inactivate the other, so the other becomes useless. Yeah. So you will automatically have 1 active assembly per hypercolumn.
That makes sense. We kind of built that into the spatial poetry, right? Mm-hmm. Another thing that's odd, it's not reflected here, is something I never understood exactly, is why do you don't see these colors randomly distributed in a column. There's a linear progression
to it, right?
And that's puzzling.
Talked about it.
Yeah, because it would seem like I'm just going to inhibit my neighbors. My neighbors would be more likely to be completely different than me than what they're very similar to me.
Right, and how does that work?
Yeah, so that's another thing I see this picture. They should be on a rainbow going across in the right order here. Mm-hmm. And one of the things that came out recently is we've been talking about grid cells in the column. Well, grid cells have a structure that has a bump, and the bump moves. Mm-hmm. And the bump moves in a direction. It doesn't jump around. It moves in a direction. And so if you think about the lower level layers in the cortical column, let's say there's some cortical grid cells in there, and they're representing location. And as that thing moves, that bump is going to move. It's going to move. Doesn't jump around. It moves in some order, in some direction. And that's what it more looks like in the supergranular layers. That's what it looks more like. You have this sort of linear. So I'm wondering if there's some interaction between like the cortical grid cells, which we have hypothesized, but I'm pretty confident they're there. They have a more, I don't know, for a better word, a linear representation space. It's a continuum, and that's what we see in the upper layers. But none of our inhibitory models, including this one, would suggest why it would look like that, a continuum in the upper layers. But I'm thinking, well, maybe these things are tied together somehow, and that maybe that continuum in the upper layers may be derived from the cortical retail. It's very speculative. But I think my point out is in a model, if we want to do a model like this, that's another thing I think that has to be explained as to why the adjacent mini columns are the most likely to be closest to each other in representation. They should seem to be the most further apart.
I think if you assume that the basket cells are not discrete but smoothly spread out throughout the sheet,
Yeah.
you would automatically get that property.
Why would that property come out of that?
Because you would inhibit, a particular feature would inhibit its neighbors,
Yeah.
but then right after that, it wouldn't be inhibited.
Oh, you're saying, what it would say is that if I have a vertical column in V1, that the next vertical columns in V1 would be
Further away, but then that happens for every feature.
But why can't it be vertical column, horizontal column, horizontal column? You know what I'm saying? Why does it have to go vertical column 10 degrees off, vertical column 10 degrees off? Why couldn't it be like vertical column here, your battery's low, horizontal column? You know what I'm saying? It forces the spacing of the vertical columns, but it doesn't.
Well, it forces the spacing of the vertical columns, but the exact same thing happens for the next orientation over.
But why couldn't it be 90 degrees at the next mini column over?
I don't think it could.
I think one thing is that the orientation is not crisp in whatever the lower level things that are detecting orientation are. So, a vertical column is going to have one stimulation. You're 5 degrees from that, you're going to get both those guys kind of wanting to respond, and you need something to make that more crisp. But you're not going to necessarily force them out to polar opposites.
But I'm saying, if you assume all the connections are learned, Kevin, it's not just some preordained connectivity. If that was the case, then you're right. If I basically have an input from the retina and it's just gradually changing as they go across V1.
I'm just saying, to the extent that you are coalescing these various orientations, they're going to look similar to each other. The adjacent ones are going to look similar to each other, are going to receive a similar type of stimulus, just out of phase just a little bit.
Well, I don't see why.
Well, I mean, any classical filter, is basically going to have overlap onto the adjacent channel.
Yeah, but these are not analog filters. These are learned patterns, right? This column says, I'm going to learn some pattern that I like to represent, whatever it is. I don't know in advance.
I'm talking about the stimulus, not necessarily the
yeah. So the question is, so let's say I have a given input and one column says that matches me really well. I'm going to learn and I'm going to inhibit everybody else. Great, I learned that one enough. Now I give another stimulus that's slightly different from it. Why would I assume that that's going to activate the adjacent mini column? Why would it? Why would it? Why wouldn't randomly some other mini column pick it up? What's forcing it to be in that 10 degrees thing? I'm missing that.
Okay, well, between maybe it's at the apocrine layer level, I don't know.
You're talking about in the retina?
In the retina, yeah.
But no, the column doesn't know what it's getting. It doesn't have no idea what it's getting. It's just getting some inputs.
Right.
And these inputs, so the retina is out of the picture. It's just getting these inputs, and it's saying, it's like the spatial pool. The spatial pool knows nothing about what it's looking at. It says, I get some input patterns. It can be all over the map, a certain dimension, and I'm just going to try to parcelate it into some n number, 10 different, first order basis function type of thing. And so it doesn't matter what the retina is doing. It's just saying, I'm going to, I guess it's still a mystery to me. It's still a mystery why the adjacent mini column, maybe Supersite might be right, but I haven't gotten it yet.
I have to work through it. That's my intuition.
It's if things are going to be similar and wired together, somebody is going to make note of that fact and strengthen that. So making things, extremely quantized is probably not in the system to the advantage of the system. Because
No, I don't think that's what Jeff is saying. They're like, why are they spatially next to each other? I think you're just giving
Oh yeah, if you're saying why would I have a representation that's 10 degrees off? Yeah, I got that.
Right.
It's why is it next to the one that's vertical? Why is it always? Why is my move across the cortex is always 10 degrees, 10 degrees, 10 degrees, 10 degrees like this?
So I guess the answer is if this orientation is being stimulated and this other one is being stimulated, where do you see those activations coming into the columns? Is there some kind of
No, there'd be just pixels coming into the column, let's say. The retina is not oriented. Retina is just on-off. You have pixels coming in.
Yeah,
No.
So may I say something?
Yeah.
May I propose some way of that?
Yeah.
So one way to think about that is to think about the connections in the microcircuit. This one, right? Because there is a high degree of local recurrent excitation. And you might arrive at a model, like the idea doesn't mean that they're going to be neighboring stimuli. But if you assume that this recurrent local connectivity actually does something, right? Which, again, I know in the current Numenta model, like you put a lot more power on the individual neuron, so there's not a lot of collaboration, there's no assemblies in that local sense. But if you allowed for that, then you would immediately see that, of course, neighboring mini columns will have some degree of recurrent excitatory connections, which will bias them towards assuming similar orientation.
Clearly, if I assume there's a hardwired connection between these guys, and it's not going to be learned, and I'm going to make more preferential connections, a driver input to the next one over, yeah, I would agree with that. But I don't
the idea of a self-organized map.
I don't see it that way. I mean, first of all, these local recurrent connections are typically the distal dendritic connections. They're not the strong ones.
Mm-hmm.
They're very weak. You've shown them there as 0.9 millivolts. I'm not sure. It's very difficult. I mean, you have to. This is why it's really, really important when someone says there's a lot of recurrent connections. Like, what are they? Where are they going on the cell? And what is their effect on that cell? Because
we're overly simplistic with that all the time.
Yeah, so I think one of the big insights we had here is that we really have to make this at least a first order distinction between, proximal and distal.
Right.
It's going to be more than that. But
and you probably also need to make a distinction between facilitating and depressing, because that's another order.
That's another thing too, which is so many damn things to keep in your head at once. Anybody says, oh, there's a lot of reciprocal connections. Yeah, I kind of get you're not being very precise about that. So I don't know. I mean, there's clearly some reason why the columns go like this and not just random all over the place. Right. It's also clear that why you would have any particular orientation, you'd seem spaced out. That was a good point. Okay, that makes sense. I think the answer to why they're gradually changing is going to be not a simple answer. It's going to be something clever and not obvious about it, but that's just my intuition. I can't prove that. But all I want to point out is that
it's clever and hyper specific.
When we talk about, I've chosen things that I care about, so maybe I'm wrong. But I find certain things jump out at me as like crying for an explanation. And one of those things is that you've got this sort of continuous thing like this. Right. The other one, of course, was the very high speed, the high speed, fast inhibitory thing we were both sharing that models. So there's a whole bunch of things, but I just want to point out that we can't be complacent and say, that explains it all. It's like, no, there's other things that are important here we haven't gotten to yet, so we might be missing some big thing.
Right. It's just from my perspective, somebody who cares for activity, right? Yeah. I care a lot for models that can actually produce activity that looks like the real thing. Yeah. In terms of the electrophysiology of these components. Yeah, and obviously we haven't really modeled electrophysiology, we modeled functional physiology. Which are two different, obviously complementary perspectives.
Yeah.
Just from a time check perspective, do you have a much more to go over?
No, I only wanted to point out one more thing. Which is this general observation. So this is the thing that the point that my collaborator, my former colleague Mikael Lundqvist made in his dissertation, right? To point out that in this transition from the ground state to some state where an attractor is firing like these fast gamma bursts, where you get these nested oscillatory effects, you get like a slow theta phase and then like fast gamma on top, right? That in fact, if this is still a balanced network, right? So there's not more spikes being elicited during that gamma burst, at least in this network model, than that were elicited before. The difference is just that now all the emitted spikes are local to the specific selective mini column, which is active for some time in this attractor, right? Whereas upon return to ground state, all of these spikes distribute again over all of the, over all of the neurons, and it's no longer specific. So you get an explanation for these rather specific gamma bursts and why they're so prevalent in active information processing. And he made exactly this point, right? That so this effect occurs, single cells in the active column climb faster to firing threshold in each oscillatory cycle, right? So when the basket cells shut them off locally, thereby shutting down competitors before they get a chance to spike and influence the network dynamics. By competitors, meaning neurons that are not inside of the currently active assembly. Of course, there is some limit to how long that assembly can be active, which depends on things like synaptic depression and neural adaptation. The neurons will tire. The transmitter required for keeping that attractor active with a few long-range interactions and the local recurrent circuit, it will eventually deplete and so the attractor will die out. That's why there is an end to every attractor. They're not attractor in the physical sense, they're quasi-attractors. And you can show that the length of these bursts and the number of these bursts converge on what has been shown in electrophysiological work when you presume sort of commonly accepted values for synaptic depression at cortical layer 2-3 recurrent synapses, for example. So you can show that.
That's a complicated summary.
Yes, I understand. I understand. Let me just show one figure. That's probably the last one then. Can I go down here? I can. So this is from the working memory model that we contrasted with the macaque data, the Journal of Neuroscience paper I published. Where if you vary the time constant on synaptic depression, then you can see that when your synaptic depression, right, recovers very fast, so you have a fast time constant, right, then you essentially get to infinitely long burst lengths, right? So you get to persistent activity of sorts. Whereas with more realistic numbers in the neighborhood of 500 milliseconds, you get these 100 millisecond long activations, which then contain multiple brief cycles of gamma. And inside a working memory model, this also depends a little bit on the memory load, because if you only have one item, then your attractor is not actually competing with other attractors. So you get very long persistent activity, which also nicely matches experimental data on single item working memory, which tends to be a lot more persistent than multi-item memory when attractors are competing for foreground. And so we match some of these things so to show that just like in macaque, the burst rate goes up with higher memory load. So does it in a theoretical model. And you can sort of like, you get a handle on some of these peculiar temporal dynamics that we see.
So if I were to take a summary from this, I'll just be honest with you, Florian, I find, electrophysiological models are a constraint on the problem, but I never found them to be useful figuring out function as much. They're more like, I have to have an explanation from in the end, but I always drive theory forward on a functional model, just as an observation line. But I would say that a couple of big things have come up in the last year or so that we didn't really discuss in depth when we were working on our work earlier. One is we never incorporated an idea of working memory into our models at all. So I think I've come to believe that working memory is sort of an inherent part of every cortical column. It's just as it's going all the time, it's remember what it just did and you can play it back again somehow. And so that's a big new insight that you've been bringing here and talking about that more. And then I think the whole gamma frequency thing is fascinating from both the thalamocortical interaction and now you're saying the upper layers here. So the idea that multiple things happen during these things, or maybe that the gamma frequencies play an important part of how the neural representations are distributed across the cortex or something like that is fascinating. So I'm going to leave it at that. I just want to point out, I'm trying to bring it up a level. Right? The physiological stuff is very hard for me personally to digest in a way that says, oh, that suggests what's going on. You can suggest why you see these spikes like that, but it doesn't tell me what the hell is the system doing. It's like, Why is it doing that? What's its computing? What's its functional computation?
Right.
I don't want to get. I think we should end this because we've got our time.
we really should.
But I'm just trying to, as I'm not arguing with you as much as I'm trying to align our thoughts.
Right.
So try to give you sort of.
Can I ask you a question before we close? Could you elaborate on this out of phase signals? You kind of mentioned, I'm trying to figure out, are you saying it's out of phase in some sort of organized way, like there's multiple of these phases, or just
No,
just exogenous from the current inhibition?
yes. You can plot a distribution of the gamma phases over the different columns, and it's just all over the place. And the point is just its broad distribution.
But you're saying the out of phaseness is a function of distance.
It's primarily a function of distance, yeah.
Okay. So
From your model standpoint, you just need something that's different in order to re-invoke it.
Yes,
Right.
exactly.
So if that was the case, and let's suppose they were separate but out of phase 360 degrees, what would that distance be? In other words, how would they? In other words, how would if things have their own gamma rate?
Mm-hmm.
If they're offset by some amount, they're going to be out of phase. I'm just wondering what the distance is for two things being in phase just by sheer distance.
Oh, if they're immediately neighboring, so you see that the gamma phase of neighboring columns are actually very close.
Right.
You see that they slightly shift. The further you go, you saw that in the plots where I sort of linearized all the mini columns. You see that they're actually they drift a little bit, and then when I go over the corner of the cortical sheet to the other side again, because I run out of the column, out of the row, then it jumps, and you're suddenly at a very different gamma phase. So they're really neighboring, or depending on your conductance speed, right? Something that is a multiple of the gamma cycle. So let's say you had a 100 Hertz oscillation, you're going to look for a connection that has a 10 millisecond delay. That means you're going to be in phase.
How far? What distance? Physical distance would that be?
Oh, something like 5 millimeters.
So how many columns apart? How many
So that's like
columns apart?
10, 20 columns apart.
Interesting. I'm just wondering if that's a mechanism that means anything, or whether it's far enough apart that they wouldn't be any relationship to each other.
Gamma synchrony is a fascinating topic, as are all synchrony and oscillations, of course. And people are working on this all the time and trying to understand. But in general, the faster the oscillation, the more local it is. Right, the slowest oscillation, slow wave, right, a whole brain phenomena.
Sure.
Whereas the fastest oscillation, high gamma, tend to be super local phenomena. And as soon as you go like a couple of millimeters away, it's completely different.
I was just kind of curious because when you see macro structures, pinwheels, across the structure, whether that phase delay that you're talking about has any structural implications.
Yeah, no, not by itself, because it's just like random, right? It's just from the fact that it's spatially distributed.
Yes.
So I mean, maybe one could build something, but the way that we've implemented it is no straightforward implication.
So you said about 5 columns up over.
Yeah, or 10. I mean, it depends on
the conductance,
the speed and the strength of the synapse, because bigger axons, are faster.
Okay.
So, I have a hunch that Jeff wants to say.
No, I don't want to talk about it. I just was making notes myself.
Okay.
I don't want to talk about it. We should probably close the meeting down.
Right.
We've gone long enough.
Yeah. Well, thank you for your attention.
Cool.
Yeah,
Thanks.
Thank you.
Hello, everybody. Oops. Okay, thanks for watching. They're offline. We'll talk to you guys later. Happy Thanksgiving if they're in the US. Thanks for watching the stream. There'll be another stream next week.